Module 1, Lesson 5 covers measures of central tendency, and in your textbook, this is section 3.2. So, a measure of central tendency is a value that represents a common or typical data item within a data set. The most common types that we have, first would be the arithmetic mean, or in this class we'll actually just say the mean when we refer to it. There are other types of means, but we're only going to be concerned with the arithmetic mean. And that's simply the sum of all data items divided by the number of items. And it's also known as an average, which you probably are familiar with. Next, we'll look at the median, which is defined as the middle data entry in a sorted data set, or the average of the middle two. And lastly, we'll look at what's called the mode, and this is the most commonly occurring item within a data set. So the reason that we have multiple types of measures of central tendency is because some of them work better in different situations than others, and we'll be looking at those situations and deciding which is the most appropriate measure of central tendency based off of our data set. Let's begin with the mean. Technically speaking, there are two different types of means. We have a sample mean and a population mean. And these formulas, you don't really need to know much about them, but just to give you a brief explanation, the x with the line above it is called x bar, and that represents the sample mean. The large E looking symbol is the capital Greek letter sigma, and in mathematics that represents a summation. The x is our representation of our data set, the data in our data set, and n is the number of items within the data set. So the sample mean is defined as the sum of all of our data items divided by the number of items. Similarly, for the population mean, the symbol there is the lowercase Greek letter sigma, and the capital N just represents a population size instead of a sample size. But both of these operations are basically the same, so we don't really see much of a difference between them right now, but later on in the class it will actually become important which one we're referring to. The mean is probably the most common type of measure for central tendency. However, there are times when it's not the best measure. First, if the data set contains outliers, the mean can be greatly biased. Since it contains information from every single data item, one value that is much larger than the rest of the data item or much smaller than the rest of the data items could greatly affect the overall mean. Also, if the data is skewed, meaning that a large portion of data is grouped together to the left or to the right, and a smaller portion lies on the opposite end, the mean can also be biased. And thirdly, if the data is qualitative, then the mean cannot be calculated. So for instance, if your data set is the words that are colors, for instance, brown, blue, green, what have you, if you try and add those words together, you can't do it. You can't take words and add them and do mathematical operations. So if your data set is qualitative, the mean doesn't help at all. Let's take a look at some examples with the mean and get a brief introduction as to how to calculate it. So let's find the mean of the following data set. I have 15.7, 21.0, 11.5, 14.8, and 16.2. So the mean is defined as the sum of all of those data items divided by the number of data items, which is 5. So if I take each of those items, add them together, find that result, divide by 5, then the sum is 79.2. If I take 79.2 divided by 5, I find that the mean is 15.84. Now, let me give you another example. The calculator is going to find the mean for you in most situations. It's good to know how to do one, However, in this class, you're going to have, fairly large data sets that you're not going to want to calculate the mean by hand. But understanding the intuition of the mean and how it can be misused is actually a really good application of understanding. So for instance, let's say we want to find the mean of each of the following two data sets. So the first data set, all of the items are exactly 1,000. So I have 5 data items that are 1,000. In the second data set, I have 4 data items that are 0 and 1 data item that is 5,000. So let's give some context here. Suppose these are data sets for the results of a lottery, and the lottery advertises everybody wins an average of $1,000. So using the term average in that way can be very misleading, because normally when people think of an average of 1,000, they think of an equal distribution of all values. So they think no matter who plays the lottery, they walk in and they win $1,000. That is one situation where you could get an average of 1,000. But another situation is part B, or the second data set there, which none of the first 4 people win anything, and the last person wins 5,000. If you take that divided by 5, you still have an average of 1,000. So for instance, in the first set, if you take 1,000 plus 1,000 plus 1,000 5 times, that gives you a total of 5,000. When you divide that by the 5 data items, you get 1,000. So that's an average of 1,000. Or in the other situation, if you add up 0 plus 0 plus 0 plus 0 plus 5,000, that's a total of 5,000. Divide that by the 5 people who played, and there's an average of $1,000 winning. So the mean can be used in misleading ways because of the large effect outliers have on the mean. Let's take a look at the median. The median has a definition that depends on the number of data items in the data set. If there's an odd number of data items, then the median is defined as the middle data entry. The data set does have to be sorted though. If there's an even number of data items, then the median is defined as the average of the middle 2, because if you list all of your data items in order from greatest to least or least to greatest, it doesn't matter how it's sorted, you're not going to have just one value in the middle. You'll have 2 values in the middle, so you just take the average of those 2, and that's your median. Now the median is used when the data set is skewed or has outliers. The reason that that is the case is because you're only looking at the one value that's in the middle of all the data entries. And so that value is the least likely to be an outlier. In fact, if there's no way that the value in the middle could possibly be an outlier, your whole data set would be outliers, and therefore none of your data set would be outliers. So it is protected from outliers, but it's still not defined for use with qualitative data. So let's take an example and say the price of homes in an area. Generally, we hear about this as a median home value rather than an average home value. And the reason is that there is very likely outliers in your data set. So for instance, if you live on the street that Mr. Burns from The Simpsons, who's, ultra wealthy person, lives on your street and has multi-million-dollar mansion, but the rest of the homes are just average priced homes. If you take the average of all of these houses, it's going to look like it costs a lot of money to live in that neighborhood. But in fact, it's about the same price as the rest of the area. It just happens that on that street, Mr. Burns is an outlier and affecting, the average home value. The median home value, however, would be unaffected from Mr. Burns. It would represent a good middle value for all of the homes. Let's take a look at a few examples where we do some calculations. But as I said, the calculator is going to do these calculations for you, just like with the mean. So you don't really need to focus too much on how to do the calculations, but the interpretation is the most important thing. So let's find the median of the following data sets. So the first data set are the values 27, 52, 16, 23, 35, 46, 49, 21, and 39. Now, I need to sort those data values. So I chose to do it from the least to the greatest. You can do it from greatest to least. It doesn't make any difference. Now, the median is the middle data entry in that sorted data set. And because there's an odd number of data values, the middle value, which is 35, that's my median. Now, suppose I have the data set 14, 35, 61, 28, 35, 44, 51, 67, 38, and 12. I'm going to sort that data set, and I'm just choosing to go from least to greatest. It doesn't matter. Now I have an even number of data entries, and so there's two values that are in the middle, 35 and 38. The median is defined to be the average of those two, so 36.5. The last measure of central tendency that we're going to look at is called the mode. The mode is defined as the most commonly occurring data item within a data set. It's perhaps the only measure of central tendency that works for qualitative data, and it's generally reserved for this use. If no data item occurs more than any other, then there is no mode for that data set. We just write the words no mode. If a data set is multimodal, meaning that more than one data item occurs with the highest frequency, then all of those items are listed individually. It's tempting to try and average them or do some sort of operation with them, but you just list them. A data set that has two modes is called bimodal. I've heard data sets referred to as trimodal, having three modes, but generally I've heard bimodal very commonly. But if you have three or more modes, you generally just say refer to it as multimodal. Let's look at some examples. So let's find the mode of each of these data sets. Now, I did say that the mode is generally reserved for qualitative data only. You can define a mode for quantitative data. It's just, you generally wouldn't use the mode for quantitative data because you have the mean or the median to use instead. But it's fine to calculate, and that's what we'll do here. So let's find the mode of each data set. The first data set is 16, 18, 20, 19, 36, 45, 51, 23, 76, and 12. Well, all of those data items appear only once, and so we say that there's no mode there. Let's do the data set with 25, 36, 41, 19, 31, 46, 28, 36, 16, and 11. In that situation, the 36 occurs twice. All the rest of the data items occur only once, and so we just say that the mode is 36. And how about one last example? The data set is 36, 39, 46, 25, 41, 39, 25, 15, 49, and 46. If you go through and look through, I definitely see 25, 46, occurring twice, but it also looks like 39 occurs twice as well. So the modes there's 3 different modes, are 39, 46, and 25. The next thing we're going to talk about is called a weighted mean. A weighted mean is a means of approximating the mean for a data set when only a frequency distribution is available. So we know how the data is distributed, but we don't know what the actual data itself is. So I'm going to walk through an example where we take a data set and create a frequency distribution from that data set, and then calculate both the weighted mean of the data set and just the regular mean of the data set. So here's my data set: 26, 35, 14, 21, 36, 42, 9, 19, 18, 28, 34, 33, 22, 26, 40, 19, 21, 17, 29, 11, and 12. Now, what I'm going to do is first just calculate the mean of that data set. So the mean of that data set is 24.38. And a frequency distribution for that data set, and I decided to use 5 classes. Using the maximum and the minimum data entry, I calculated the class width of 5 classes, created my classes, and put everything in as a frequency distribution. So the actual mean is 24.38. So I want you to recall that in a little while, because we're going to compare the value of the weighted mean that comes only from the frequency distribution to the value of the actual mean of the data. And that way we can compare and see how accurate this process is. All right, so going forward, we're only going to use the frequency distribution. So first, we fill in our distribution with the midpoints and a column that multiplies each class midpoint by the frequency. So I went ahead and did that. So I took my classes, the 9 through 15, 16 through 22, 23 through 29, 30 to 36, 37 to 43, and I calculated the midpoints of each of those. And that was 12, 19, 26, 33, and 40. I had frequencies for each of those classes. There were 4 data items between 9 and 15, 7 between 16 and 22, 4 between 23 and 29, 4 between 30 and 36, and 2 between 37 and 43. Next, what I did is I multiplied all of my midpoints times my frequencies. So 12 times 4 is where I'm getting the 48 from. 19 times 7 is the 133. 26 times 4 is 104. 33 times 4 is 132. 40 times 2 is 80. Then we're going to start adding some things up. So we add up the total. The total of the frequencies is 21. The important thing about the sum of the frequencies is that that's always going to equal the number of data items in the data set. And when you're doing a mean, you need that in your denominator, the number of data items in the data set. And you can always get that from the sum of your frequencies. Next, I'm going to add up the sum of the midpoints multiplied by my frequencies. So all those values that I found, I'm going to add those together, and that gives me a total of 497. Then the weighted mean is found by taking those totals and dividing. So 497 divided by 21 is 23.67. So the weighted mean is quite close to the mean of the data set, which was 24.38. It's not very far off at all. And it's impressive because as I said, when calculating the weighted mean, we didn't actually have the data set itself. All we had were the distribution of the data instead of what the data itself was. The reason this works is because the data contained in each class is usually well distributed, allowing the midpoint to be a good approximation to the original data set. So let me give you the data set again, but this time I'm going to sort it. The first class was 9 through 15. Now, the midpoint of that class is 12. So the original data set, all the values between 9 and 15 were 9, 11, 12, and 14. What we did is estimated those values with the value 12 each time. And it's perfectly fine in terms of a mean to estimate values, because in the mean, only the total in the numerator really makes a difference. It doesn't really make a difference what the individual values are. So 9 plus 11 plus 12 plus 14 has a sum of 46. Now if I estimate 9 as the value 12, and estimate 11 as the value 12, 12 as the value 12, and 14 as the value 12, that has a sum of 48, which isn't altogether different from the sum of 46. It's just off by 2. And it's entirely possible that in a later class, using the midpoint ends up being an under approximation, which cancels out this over approximation. So that's why this ends up being a good measure and a good approximation to the mean of the data set itself. For example, course grade. Often an instructor will designate a set of weights to parts of a student's course grade. For example, a final exam may be worth 25% of the course grade. The average of a set of quizzes may be worth 15%. The average test grade may be worth 40%, and so on. These weights can be thought of as frequencies, and you can use the grades on each assignment as the midpoints, and that using that weighted mean process that we just developed, you can get what your actual course grade is. And this is how many instructors actually do your course grades. So let's try an example. So a student's grade in a particular class will be determined using the following set of weights. Using the grades the student received, calculate the overall course grade. Okay, so this student had some different categories here. So the homework was worth 5% of the overall grade, the quizzes was worth 10%, the attendance worth 10%, and the exam average worth 50%, and the final exam worth 25%. These weights need to add up to 100% to make sense with the course grade. Now, this particular student scored a 90 on the homework, 75 on the quizzes, 100 on the attendance, 87.5 on the final exam, the exam average, and 78 on the final exam. Now, if we multiply each of those grades times their weight, for homework, 90 times 0.05 is 4.5. 75 times 10%, or 0.1, is 7.5. For attendance, 100 times 10%, 10. Exam average, 87.5 times 0.5, or 50%, is 43.75. And the final exam, 78 times 0.25, is 19.5. Now, to get a weighted mean, we need to add up both the weights and the column that multiplied the grade times the weights. So the sum of these columns, the weights add up to 100%, and the grades times their weight is 85.25. Now, if we divide, we're only dividing 85.25 by 1 because 100% is equal to 1. So we don't really need to do that step in this example. So the course grade is actually 85.25, which for this particular student, it looks like they have a B. GPA is another example of where weighted means get used. So a student's grade point average is calculated using a weighted mean as well. The number of course credits or hours per week are used as weights, and the grade is used as a midpoint. Since a letter grade is ordinal data, which is qualitative, it must be converted to something that is quantitative in order to perform any calculation. This is done by a point system. So an A is worth 4 points, B is worth 3 points, C is worth 2 points, and a D is worth 1 point, and an F is worth no points. So let's take a look at an example. The following table represents a particular student's transcript. Use this to find the student's GPA. So the student has a history class with a grade of B, that was 3 credit hours. Art class with a grade of A, that was 1 credit hour. Math course, which is a grade of A for 3 credit hours. English with a grade of C for 3 credit hours. Computer literature with a grade of A for 1 credit hour. Psychology with a grade of B for 3 credit hours, and physics with a grade of C for 4 credit hours. So what we do is we code each of the grades into the grade points. So the B in history is worth 3 points. The A in art is worth 4 points. The A in math is worth 4, and so forth. And then we multiply the grade points times the hours. So 3 times 3 is 9, 4 times 1 is 4, 4 times 3 is 12, 2 times 3 is 6, 4 times 1 is 4, 3 times 3 is 9, 2 times 4 is 8. Now we start adding up the appropriate columns. The sum of the hours is, this is what we're using for weights, is 18. The sum of the points multiplied by the hours is 52. So the GPA here is 52 divided by 18, which is 2.89. Estimating weighted mean. You can estimate the value of a weighted mean if you have a histogram available. If you visualize the histogram bars as a set of weights, the point where the weights would balance is where the weighted mean would be located. So for example, this particular histogram, this would be the center of my distribution, but if I tried to put a balance point right here, between the 35 and the 45, there's more weight on the histogram to the left than to the right, so it would fall over. So if I move my mean over a little bit, it would probably balance somewhere, say about right here. And so that's the balance point, and that's where that weighted mean would be located. So you can always estimate the location of a weighted mean that way. And it turns out that this weighted mean is at 34.58 if you do the midpoints into a table, the frequencies into, if you create a frequency distribution from this graph and calculate, that's what you would get. 34.58. Shapes of distributions. Distributions are categorized based on their overall appearance. We have symmetric distributions. Symmetric distributions are such that a line can be drawn, parting the distribution into mirror images. We also have non-symmetric distributions. Let's look at the different types of symmetric distributions that exist first. So we have uniform, bell-shaped, and non-bell-shaped curves. Then for the non-symmetric, we have skewed to the left and skewed to the right. And let's take a look at an example of each. Uniform data is such that the frequencies or the heights of the histogram bars are all approximately equal to one another. Bell-shaped data is data where most of your data is in the center, and the data tapers off if you go to the left and the right of the mean. Because again, you can estimate where the mean would be, and since this is symmetric, the mean would be right in the center. But it has a general bell shape to it if you kind of picture that. Anything that's symmetric but has another type of shape, we generally just call non-bell shaped. Simply because there's lots of different ways you could have symmetric data, but bell-shaped and uniform are really the most important types. If it's data that is skewed to the left, then you have a large clump of your data on the right-hand side of your distribution and an elongated tail on the left-hand side. So it's a little bit confusing at first, but the skewness is defined by the location of the tail of the distribution, which is on the left in this case. Or, as in this case, I have the inverse of the last graph, which I have a large clump of data on the left-hand side of the distribution and an elongated tail on the right. And so this is data that is skewed to the right. Example 1. Find the mean, median, and mode for the given set of data. So I need to plug this into my calculator, and in order to put a set of data into the calculator, what we need to do is go under what's called the list editor. So under the stat button, and the very first option that shows up is edit, and that is our list editor. There's 6 predefined lists in the calculator, labeled L1 through L6. And unless you have a really good reason to do so, it's best just to stick with those default lists. Because if you'll notice down here, you have L1, L2, L3 in yellow, and so forth. And you can access those lists very quickly through those keys. Now, the data just goes into one list here. I'm going to start with the first data item, which is 19, and I just type it in and press enter, and it goes wherever the cursor, the shaded in part here is, and press enter, and then 19 appears in my list. The next value is 51, press enter, put that in, then 25, and I keep doing this until I get through all my data. 11, 8, 21, 24, 53, 14, 38, 33, 18, 44, 19, 59, 42, 38, 16, and 29. And once you have all that data in, you should go back through and double check to make sure you've entered the correct data and haven't mistyped anything. And once you're sure of that, then let's go ahead and get started with how to find mean, median, and mode. In order to perform calculations on an entire set of data, you have to use built-in functions for the calculator. If you press second and quit, so the mode key, if you'll notice up in yellow, I have the quit. So anything I want to get to a function, anytime I want to get to a function that's yellow, I press the second key first, and then that particular key. All right, so second and mode will quit out of the list editor, get me back to the home screen. The home screen is where you would just do, basic operations. It performs just like a regular calculator. In order to do a more advanced function, those are generally found under these keys, and the different available functions are listed for you. So under stat is where we're going to find most of our options. And the first item, the first menu here, gives you things that allow you to do editing. The second item is calc, and the very first option here is oneVarstats, and that's actually what we want. oneVarstats is the function we're probably going to use most on this first test. Now, before it actually runs the function, it puts the function on the home screen first, and it allows you to type in the name of the list that you want to run the oneVarstats on. If you've already got your data in L1, you don't need to hit second and 1 because you get that L1 by hitting, it's in yellow, so hit the second key first. It will by default use the data in L1 if you don't specify anything. Since we put it in L1, I'm just going to press enter, and it will find a lot of information for us. The very first option, or very first item that's shown here, is the X bar. And if you recall, we said X with a bar over it was a sample mean. Now, the mean that we are working with here, it's not specified whether we're using a sample or a population to start with. If it's not specified, just assume it's a sample. It's a much more rare case that you're working with a population of data. And if you'll recall, we also mentioned that in the calculation of a sample mean versus a population mean, the calculation is basically the same. So whether you have a sample of data or a population of data, you'll always get the same answer. So I'm just going to take this to, say, 2 decimal places. So I'm going to call my mean 29.58. And that's just listed here. So if you have a population of data, you would use this value. If you had a sample of data, you would use this value. The rest of this output, if you'll notice the Greek letter sigma, the capital sigma here, this means the sum of your data. So if you added up all the data items together, you would get 562. The next item is the sum of the squares of your data. So if you had gone through and squared each of your data items and then added, this is what you would get. These next two we'll talk about when we get to the next section. N is just the number of items that were in your data set, but right next to the N is a down arrow, meaning that if you press the down arrow on your calculator, you're going to see more output. So you have the minimum data entry that was in your set, Q1, which we'll look at later. Next we have the median, so the median is 25. And the nice thing about that is, when you come up with a median, it's defined as the middle data entry in a sorted data set. Well, I didn't sort my data set, but the calculator knows that it has to be sorted to get the median. So it sorts it for you in that calculation. Q3 is something that shows up and we'll talk about later, and then the maximum that it finds is 59. One thing that's not listed here is the mode. And so in order to get the mode, we kind of just have to go through manually and get it. The reason the calculator doesn't give the mode is because it is generally an operation that is reserved for qualitative data only. And our calculator doesn't allow us to work with qualitative data. So it just doesn't do a mode. There are things that it could do to help us though. Like for instance, above the stat key, it says list. So you can do some different operations on lists. Like for instance, here's your operations menu. You could sort your list. So if I wanted to sort my list ascending, so that's what the A means. Just give it the list you want to sort. What it does is it sorts it and puts it back into L1. So I need to go back to my list editor to see it now. And you can see that the data is sorted. And the advantage there is now you can see, okay, 19 occurs twice. So that's probably a mode. And 38 occurs twice. And the rest of them only occur with frequency of 1. So the mode here, this is a bimodal data set, 19 and 38. So that's how we'll use the calculator to find mean, median, and mode for a given set of data. Now, your homework and tests, should specify a number of decimal places to round to. I didn't specify that here because I'm talking to you, so it doesn't really make a difference. And it should also specify if it's a population versus a sample. However, if it doesn't specify, you can always assume that it's a sample of data. Number 2, calculate the weighted mean of the following frequency distribution. Okay, I've got a table here with a frequency, a set of classes and frequencies. The first class is 10 through 14 with a frequency of 10. The second class is 15 through 19 with a frequency of 13. Third class is 20 through 24 with a frequency of 8. The next class is 25 through 29 with a frequency of 4. And the last class is 30 through 34 and its frequency is 1. Now, I purposefully didn't clear out my list here because I want to show you how to do that as well. So this is the data from the last problem, and I need to get rid of it so that I can start putting stuff in for this next problem. One thing you can do, you can highlight data items and you can delete them one at a time using the delete key. However, that takes a long time. Another thing you can do is actually, if you scroll all the way to the top, you can highlight the name of the list and you can press clear and enter. You have to do clear and enter because if you hit delete, the list just disappears from the list editor and you just can't access the list anymore. You can always get that back. You will at some point do that, and that's okay. You can always set up your editor back to the factory defaults. If you go to Stat and Set Up Editor, the last option here. So I'm just going to press enter. I enter twice, it'll say done. And if I go back into my list editor, list 1 is back again. All right, so to clear out a list, you need to do clear and enter. And it'll erase everything all at once. Now, a weighted mean, as we learned in the lesson, we need to have the midpoints of our distribution along with the frequencies, because we take the midpoints times the frequencies, sum up those columns, and divide. So let me put in a new column for midpoints. There we are. Now I need to figure out what those midpoints are. So I'm going to get out of my list editor by hitting second in mode, which gives me the quit function. And like I said, that'll get you out of just about anything. I'm going to hit clear on my home screen just to get a nice, fresh home screen here. To find any midpoint, you're taking the average of the individual class ranges. So 10 plus 14 divided by 2. Whoops, I didn't hit divide, did I? So 24 divided by 2. And I get 12 for the first midpoint. So I'll just put that in right there. Now the next midpoint, 15 plus 19 divided by 2. I get 17. So I'm going to put that in right over here. And if you'll notice, 17 minus 12 is 5, 19 minus 14 is 5, 15 minus 10 is 5. The class width of this distribution is just 5. And so if you find the very first midpoint, you can get the rest of them simply by adding 5 repeatedly. So 22, and then 27, and lastly 32. Now, have my midpoints. I need to put midpoints and frequencies into, I'm going to put these into L1 and L2. So the midpoints will go into L1 and the frequencies will go into L2. And we're going to use one-var stats again, but we're going to use it in a different way. So let's get started just putting the data in. So set up my list editor. My midpoints, 12, 17, 22, 27, and 32. Then the frequencies go into L2. So I have 10, 13, 8, 4, and 1. And what I'm going to do in order to get the calculator to use both lists together, I'm going to hit second and quit. And now what I will do is still hit stat, and I still go over here to OneVerstats. Okay, but OneVerstats can work in two ways. It can either find mean, median, and all the other statistics it does for a single set of data, or for a frequency distribution that has a midpoint list and a frequency list. So if you put the location of your midpoints, so L1, then a comma, and the comma is right above the 7. You don't have to put shift down or anything like that. Then L2. So now I have OneVerstats L1, comma, L2. It will interpret the first list that you give it as midpoints, and the second list that you give it as frequencies. So now it's going to do a weighted mean. So now the weighted mean of this distribution is 18.25. And I didn't need to multiply midpoint times frequency, add up those, add up the frequencies, and divide. If I had done that, then that would have given me the same answer. It's just that it's not necessary here because you can use the calculator to help you out. A couple things to keep in mind when doing this, however. It's very easy to type in all of the data into L1 and L2. Okay, and then when you actually run OneVerstats, to completely forget to do L1, L2. And it's going to run. But when it does, it's only going to give you the mean of your midpoints, because that's what's in L1. It will always default to just L1. It won't know that you've put the data into L2, meaning that you wanted those as frequencies. So you need to be very careful. One way to check for this is if you look at N, this tells you how many data items it included. Well, this calculation included 5 data items. Well, the frequency of the first class is 10. So there's already more than 5 data items in the data set. So if you use the OneVerstats L1, L2 and turn it into a weighted mean, now N is 36, which is the sum of these frequencies. That's really the only way to kind of check after the calculation that you've done this correctly. And the other thing that I want to mention is it's actually relatively simple to do a weighted mean without the use of the OneVerstats. But later on, when we start looking at standard deviations, a weighted standard deviation is actually a very complex calculation, and using the calculator to do that for you is going to make your answers much more accurate. And I highly recommend the use of that. But the way that you get those is the exact same way that you get the mean in the first place. So I recommend just use the calculator's features to get both the weighted mean and the weighted standard deviation. Example 3. Find the mean, median, and mode of the following distribution. So now I have a distribution of eye color and frequency. So suppose we've done a survey and asked individuals, to indicate what their eye color is, and we've just compiled those results as frequencies. So the results are brown, blue, and hazel for this sample, and the frequencies are 25, 4, and 9. To find a mean, the knee-jerk reaction here is to look and find numbers, and then add them together and divide by the total number of numbers. So if you took 25 plus 4 plus 9 divided by 3, you would get a number. It's not the mean of your data set, because your data set is not the numbers 25, 4, and 9. Your data set is a list of words: brown, blue, hazel, brown, brown, blue, and so forth. So if you want the mean, you have to take brown plus blue plus hazel plus brown plus blue and so forth divided by the number of words you have in that data set, and come to the conclusion that you can't do that. Because this is qualitative data, you can't find the mean. So in this situation, the mean is just undefined. So you can either say undefined or just write no mean. It doesn't really matter, just as long as you indicate somehow that it just doesn't exist. Be careful not to say 0, because you're actually saying that, if you added up all the data items divided by the number, then the result is 0. So an average of 0 has a meaning, but you need to say there's no mean, it's undefined, something to that extent. Same thing for the median. The median, the problem here is, in order to find the median, you would need to sort your data set. Well, how do we sort our data set? This is not only qualitative data, but it's actually nominal as well. There's no natural sense of order to the data set, and therefore there's nothing that we can do in order to sort the data set. So there's no way we can define a median. And lastly, we come along to the mode. Well, if you'll recall, the mode was defined as the only measure of central tendency that applies when you have qualitative data. So in this situation, that's exactly what I have. My data is qualitative, and so I can answer with a mode. And in this case, the data value that appears in my data set the most is brown. So that is the mode of my data set. So because I have qualitative data, the mean and the median are undefined, and then the mode is just the one that appears the most. And in this case, it's easy to find because I'm already given the frequencies. Number 4. Which of the following histograms has the greatest mean, and which of the following has the least mean? Now, if you look at the different histograms here, none of them have any labels. What we're going to just assume is that the bottom axes are the same, so we could assume that it's 1, 2, 3, 4, and 5, and that the frequencies are all equal as well. So 1, 2, 3, 4, 5, 6, 7. We'll assume that it doesn't really matter what those labels are. We'll just assume that it's the same through all of these data sets. Now, in order to answer this, there's a couple of clues that were given throughout the lesson. All right, first is that you can estimate the value of a weighted mean by looking for a balance point if you assume that the histogram bars are a set of weights. So if you have a mean that is, or a distribution that's symmetric, like in B, which is close to bell-shaped here, then the mean is going to be located right in the center, because this is where this would balance. Because there's as much data to the left of the mean as there is to the right of the mean, which means I'm going to have the mean right in the center. Same thing in part C. In this graph, the data is symmetric again, so everything would balance right in the center. Now, let's go over here to D. In D, if I tried to put my balance point in the center, then the problem here is everything would kind of fall to the left, because there's more data values on the left-hand side than there is on the right-hand side. So in order to keep it balanced, I would have to shift my mean over just a little bit to the left. And when you shift something to the left, just think of how everything's ordered on an x-axis or a mathematical axis. It's ordered from least to greatest. So that would make this mean a little bit smaller. So if in B the mean is 3, so 1, 2, and 3. In C it's 3. In D it would be like, maybe this was 1, 2, maybe it's like 2.5, maybe a little bit less than 2.5, but somewhere less than 3. In A, the same is true. This is going to be skewed to the left, but you have majority of your data over here on the right-hand side and a tail of the distribution on the left. In order to keep this balanced, you would have to shift your mean up just a little bit. So maybe if this is 3, then like, I don't know, 3.5, 3.75, something to that effect. And that would be the largest mean of all of these distributions. So the greatest mean occurs in chart A. The least mean, as we just discussed, occurs in chart D.